And Ali is trained as an applied mathematician and control theorist, and I will turn it over to you.
Thank you, Patrick. Okay, so due to kind of a very intimate nature of this seminar, if you have any questions at any time, just interrupt, okay? And I will try to make it as clear as I possibly can. Okay, so what am I going to do here? I'm going to tell you about how to design optimal experiment for vector-valued Ornstein-Uhlenbeck processes. So what is this talk about? So here's my kind of motivational slide that perhaps is a better motivation for engineers than for statisticians, but let me go with this nevertheless. So imagine that you have an agent or a particle or anything like this that moves in the plane, and its position is described by this variable x of t, so it's in R2, and x of t evolves according to this stochastic differential equation. dx is ax dt, matrix. Here, this term bu is a control. We're going to quickly forget about this in this talk. And then you have some noise that enters the dynamics. And you get to observe the position here through a camera. So what does a camera do? It just takes its visual field, projects it onto a one-dimensional plane here, because I have a simplified model. This is 2D, this is 1D. Otherwise, it would be a two-dimensional plane. So we can write the position, projected position or measurement signal using this linear equation. dy is c, think of c as a row vector, multiplied by x, that's our projection, plus some noise. And now the goal, of course, is to reconstruct the position x, given the knowledge of the process y. So we observe this projection, and I want to know where the particle is. So this is a very classical problem. So now there are two things here that we need to answer. First of all, given the process y of t, how can I reconstruct x? So that has been done by Kalman in the 60s. I'm going to come back to this a little later.
Do you assume that you know the matrix A and
Yes,
G?
we have to know A, B, and G
Yes.
for the Kalman filter. Otherwise, it's a different problem, the identification problem. So provided the model parameters and the observation, how can we reconstruct x? And the question I care about here is how to choose the best C in order to have the most precise estimate of x. Okay? So here a bit of terminology. I'm going to call x of t the state process, y of t is a measurement process, continuous time here. We could do things in discrete time, but continuous time is a bit simpler. And C, the matrix C here, is going to be called the sensor. So the sensor provides us with the measurement. So I'm going to often refer to this problem as the optimal sensor design problem. Okay, so this is actually used in plenty of application. Of course, whenever you want to put sensors, you should ask, where should I put them to get the best estimate that I can? So here, physiological sensors for environmental engineering. This was some work actually that was done at Harvard where people tried to, that was some kind of special shoe for people who were in re-education or the elderly. So you wanted to use these to try to predict when they would fall. So they tried to guess where to put the sensor here so that when you get these signals, pressure points when you walk, when can you predict whether you're going to fall or not? And actually, the answer was it's very difficult. I don't ever think they got a working prototype, which is kind of strange, but apparently there are so many options when you walk that trying to distinguish when you're going to fall or not is actually quite difficult because walking itself is an unstable process. Okay, so there is an abundant work in the literature on optimal sensor, and here I mentioned actuator. I'm going to say you can say very little about this, but just because it's dual, so I'm going to give you a bit of information about this as well. It's a dual problem, sorry. So there is a lot of literature, and most of it is ad hoc. People start with a problem, try some methods, and come with some results. So here we're going to show that we can actually obtain an exact optimal placement. So this is what this talk is about. Okay, so a short outline. I'm going to tell you right away about the optimal actuator design problem, entirely similar to the optimal sensor. Then we're going to forget about this. I'm going to then describe the main results and then delve a little bit more deeply into the proof. Okay, so I told you about the optimal actuator placement problem. So here is a dual problem. Mathematically gives rise to the same problem, but there is nothing stochastic here. You have what's called a finite dimensional linear system. X dot is AX plus BU. U is called the control, B is called the actuator, and this is the state, evolves according to linear dynamics. And the goal in control, of course, is to design this U of t to make your system, described by the state X here, do something that you want. Okay? So we call B the actuator of the system. One very common way to design control is to try to find the control U that will minimize this functional. X0 here is the initial condition of the system, and you want to minimize this infinite horizon functional. We're going to take the matrix Q here to be symmetric positive definite. So you see that this somehow stabilizes the system. By stabilize, I mean drives the state X to 0. Because if X at infinity does not go to 0, this integral diverges. So what these controls do somehow is drive the system to 0. You can decide how you want to drive it to 0 by choosing Q appropriately. You can put some emphasis on some directions by changing the entries. And you want to do this by minimizing the control effort. Think of this U squared as the control effort that you need to apply to stabilize your system. Okay? So now the question, of course, this J here will depend on B in a very implicit manner, because you see that X of t, once you solve the equation, well, B is going to enter here. So this depends on B implicitly, and you can ask the same question. How can you choose the actuator B that minimizes J? That is the optimal actuator placement problem. And it can be shown to be entirely similar to the optimal sensor placement problem because of some facts of linear system theory. But we're going to use the formalism here of optimal sensor design, optimal sensor placement problem. Okay, so going back to the problem, here we're again with a stochastic differential equation. As I told you, we forget about the BU. If it's still there, I mean, we can do a change of variable to get rid of it. U is supposed to be known. So we have this process, and we have here an observation process. W and V are independent Wiener processes. As I said, we're going to call C the sensing matrix of the system or the sensor. I'm going to denote by K the expectation of the error. So X hat is my estimate of X given my past observation. So it's X hat of T. So everything here depends on T. And so this is the correlation, cross-correlation matrix of the error at time T. So what I want to do is to choose a sensor that would minimize this K. Okay, so first of all, how can we obtain K? Well, there are of course many estimation procedures for X given Y, but the MSE, the MAP, the maximum likelihood, all of these coincide in this case, are given to us by the Kalman filter. And here is how it goes. So as Svante mentioned, we need to know A and the C for this. But given that you know A and C, how to obtain the best estimate X, X hat of X, you just solve this stochastic differential equation. So A is known, X hat is your estimate, and you see that your observation enters here. So you can think of K here as giving you a gain between what you observe, again multiplying, what you observe, and what you think you should observe, right? So Cx hat is what you think you should observe because we're supposed to observe Cx. So you take here this difference, it's called, if you want, an innovation process, and this will drive the system here, and that gives you the best estimate X hat. Now, how to find K? You can show that K obeys this quadratic equation. That's called the Riccati equation. So K A transpose plus AK minus K C transpose C. So this is, C was a row matrix, so this is a square matrix, an outer product. Okay. Plus G transpose is equal to 0. And so this is not a completely trivial fact, but this matrix, this gain here, K, is the covariance of the error, as I mentioned before. So it is the same quantity that shows up here, that is a covariance of the error. And so the expected error is just a trace of this matrix. Okay? So Now, to rephrase mathematically what is problem we wish to solve, the optimal sensor design problem, well, we want to minimize a trace of k, where k obeys this equation. And you can see now that the solution k will depend on c implicitly. Here I add a parameter L. So this is in case instead of estimating all the variable, you focus, say, on the first variable, you can adjust L to minimize the estimation error only for this variable. Okay, so now there is obviously a trivial solution to the problem, which is increase the norm of C. What does that mean? Let's look at the observation equation here. If this has a fixed variance, if the norm of C increases, we have a very good signal-to-noise ratio. So you have very good measurements. So the problem will tell you, yeah, if you want to have a better estimate of the state, get better measurements like this. So we're going to try to get rid of this solution. But we should make sure to observe that it is here. It just says better sensors, better estimation. And this property actually has been studied and formalized for, I guess, 20 plus years now. And here's the most general result in this direction. Okay, so this is again our Riccati equation. K is the expected correlation, cross-correlation of the error. So what have people done? They've put here a matrix R, positive definite, and what have they shown is that the trace of K is monotonic decreasing with respect to what I call the signal-to-noise ratio, which is here the matrix R. So think of C as being fixed in norm. If R increases, you can think of putting R here in the C's, that gives you a larger C. And when R increases, trace of K will decrease. So that just formalizes or proves somehow mathematically the obvious statement that if the signal-to-noise ratio improves, you have a better estimate. So many more things have been proved along this line. There are entire books about the Riccati equation. I'm not going to go through all of them, but there are some very strong convexity properties in the sense that if R1 is larger than R2, as positive semi-definite matrices, you can show that K1 will be smaller than K2 as positive semi-definite matrices. So you have a very strong ordering. The Riccati equation tends to have a lot of very nice properties. Okay, so that rounds up here the trivial solution. So what we're going to do now is fix the SNR. So fix signal-to-noise measurement. What is the best sensor? How to obtain it? Okay, so some related work. I'm going to go quickly through this. A lot of application-driven settings, as I mentioned, and a lot of work in numerical methods and in the infinite dimensional case. So you have systems described not by differential equations, but by stochastic PDEs. And as you can guess, the results here are far more, well, they're not very advanced because it's just much more difficult. The state of the art is just to prove that the optimal sensor does exist. We have no idea of how to find it. Okay, they have a bit of a problem, so let me show everything here. Okay, so I said we're going to fix the SNR. This is how I do it. I take my matrix C. I'm going to normalize it. If C has P rows, I want to have the norm of C to be equal to P, and I call that P bar. And I'm going to play with the norm using this parameter gamma. So I just think of this as a polar decomposition of C. Unit norm, and this is the radius. Okay, angle, radius. And I'm going to make one additional assumption, is that if C has several rows, so I have several sensors, I'm going to require that they are orthonormal. This is actually a restrictive assumption, and we're going to say a few words about this later, but we're also going to care a lot about the case P equal 1. We have a unique sensor. So this is the identity, P by P identity matrix. So the set of such matrices in RPN that satisfy here this relation is called, well, the Stiefel manifold, the set of orthonormal P frames in Rn, and we're going to denote it by St of Np. So a set of P rows that are orthonormal to each other. Okay, again, what is the optimal sensor placement problem now is gamma is fixed, that is a signal-to-noise ratio. C is normalized, so it belongs to the Stiefel manifold. Minimize a trace of LK, estimation error, given that K satisfies this equation. And here we have to play with L and Q are positive definite matrices. Okay, so finally I'm going to describe the results that we have. So L, as I said, symmetric positive definite. I'm going to denote by big C the outer product of C transpose and C. So square matrix of low rank. And I'm going to define J of gamma C to be the trace of LK, where K satisfies this. So estimation error is J of gamma C. That's my sensor, normalized. This is the SNR. I'm going to call a sensor critical if it is a critical point of this function, and optimal if it's a global minimizer. We're going to be after the global minimizers, of course. Tiny bit more terminology. If M is a symmetric positive definite matrix, I'm going to call the p-dimensional invariant subspace of M spanned by the eigenvectors corresponding to the p largest eigenvalues, the highest p-dimensional invariant subspace of M. That's a mouthful, but M is symmetric positive definite. Diagonalize it, take its p largest eigenvalue and the p corresponding eigenvectors. These form the highest p-dimensional invariant subspace. Pretty natural, I believe, definition. Okay, so we're going to show that an observation matrix is critical, so not optimal, critical, if its span is an eigenspace of this positive definite matrix, the product of K, R, and K, where K satisfies this Riccati equation, and R satisfies this equation. So this equation may look a little bit nasty, you see depends here on R, but it's actually a fairly canonical equation, at least in control. It's a Lyapunov equation. Notice that it is linear in R, and you can find closed form solutions for this equation. So it's not as nasty as it looks. So this is a nice characterization, but not entirely satisfying, because I say C is an eigenspace of this matrix, but notice that this matrix depends on C. So you cannot compute it before you choose a C. So it's kind of a way to just check, a sanity check. If you obtain a C, you believe it's optimal, compute this matrix, which depends on C, and you will observe that this is indeed a eigenspace of this matrix.
You said characterization, but this is not an if and only if, is it?
It is, sorry, an if and only if.
Oh.
Yes. Should have been perhaps a bit more precise. So here's something a bit more interesting. If L and Q are still positive semi-definite, now I'm going to take P equal 1, have a unique sensor. Gamma is equal to 0. Gamma cannot be too big, you'll see why a bit later. And A stable, I've not used this terminology here yet, but by A stable, I mean that all its eigenvalues have a negative real part. So the uncontrolled system naturally goes back to 0. I'm going to say a few words about the unstable case, but this assumption of stability here is actually quite important. If A is not stable, the problem becomes far more complex in a way that we understand, but just it will be difficult to solve for everyone when A is unstable. So there is a unique optimal observation matrix. So this is already a better news. Now in the P case, in the P sensor case, we can still show there exists a unique optimal observation matrix. Moreover, it will correspond to the highest p-dimensional invariant subspace of M. So in the case P equal 1, by the way, this also holds. So the optimal C was corresponding to the largest eigenvalue here of the matrix M, which was KRK. I'm going to tell you a little bit in the next slide how to actually find the optimal, because right now we still don't know, we just know it's unique. Okay, so this requires a bit more background, but I'm going to quickly go through it. You can show, or perhaps I'll come back to this later, but you can make some very nice connection between the function we're trying to optimize and the topology of the Grassmannian. So you can show that if you count the number of critical points of the function trace K, and you differentiate them according to their signature. So you look at the number of positive and negative eigenvalues of the Hessian at this critical point. You arrange them nicely in a polynomial like this. you obtain the Poincaré polynomial of the Grassmannian. So you can think that this function actually was a perfect Morse function. There is a bit of a twist, is that this is the complex Grassmannian, and we're working over the real. So there is something here that is missing. Finally, how to obtain actually the optimal sensor? You just flow this equation. This is a differential equation, deterministic. C is a matrix. You let M of C be, well, as was defined before, KRK, where K was a solution to the Riccati equation, R a solution to the Lyapunov equation. So you can obtain M of C by just solving these two equations. And you solve this equation here, where the bracket is a Lie bracket. So A bracket B is AB minus BA. And you just initialize this ODE at a random point, let it flow, and the C you obtain will be the optimal observation matrix. So this gives us an algorithm to find the optimal sensor. Okay? All right, so this somehow, yes, basically solves the problem of optimal sensor design. A few things here that I'm swiping under the rug is that you can think, well, does this keep the norm constant? Yes, we're going to see that it has all the nice properties. So, okay, I think I wanted this slide to be the next. So, okay, should we optimize in the first place, you can ask. If I give you a system, if I take a random sensor and I compare its performance to the performance of the optimal sensor, is there actually much of a difference? So I just quickly ran these simulations and it appears that yes. So these are over 100,000 random draws for C of a fixed norm. Here I chose two matrices A of dimension 3, and I just compared the ratio of the performance of the optimal sensor by the performance of a random sensor. So sorry, it should actually be the opposite. I just looked at the trace of K, so the approximation error for a random sensor, divided by the approximation error for the optimal sensor that I had found using my method. And this is just a distribution over 100,000 draws. So you can see, so I clicked at 10 here, because sometimes the performance can be much, much worse. But you can see that for a fair amount of sensors, the performance is at least 10 times worse. That's the trace of the worst of the random versus the trace of the optimal. For many, here we're actually fairly close, and here we have the distribution. But you see that you have a fair chance to pick a sensor that performs, let's say, 4 to 10 times worse than the optimal sensor. And here are different type of distribution. This is for a 7-dimensional system, 11-dimensional system. So you see that for some system, it's rather well behaved, and you don't have this kind of heavy tails that you see here or here. I did not spend much time trying to understand here what would cause this type of shapes, but there seem to be 2 or 3 typical shapes that we see in the performance of the optimal sensor versus a random sensor. Okay, so here, let me come back to this slide. How are we going to approach the problem? First, we're going to try to write the optimization problem formally. And for that, what's going to be important is defining what the space of sensors is. And then we're going to do something which is actually pretty straightforward. We're going to compute the gradient of the cost function and analyze this gradient. So we're going to find the critical point, evaluate their signature. And recall, signature of a critical point is the number of positive eigenvalues of the Laplace, of its Hessian second derivative, and the number of negative eigenvalues, and then the number of zeros. So it's a triplet. Here's an example, function from R2 to R. This point is a maximum. Its signature will be 0, 2, 0. Here you have a minimum, 2, 0, 0, 2 positive eigenvalues, 0 the other. And the saddle will have something mixed. If you have a non-trivial number of 0 eigenvalues, we're going to call this critical point degenerate. We don't like degenerate critical points, but you can show, well, we'll be able to show that in this case, they're all non-degenerate, all the critical points of trace of K. Okay, so let's make a few very simple observations. First, so we're going to assume that the norm of C is fixed to 1. We're in the case of one sensor. it's easy to see from the definition of K, perhaps I should write here, the equation that K obeys minus K C transpose CK plus Q is equal to 0. So if I replace C by minus C, nothing changes. So that immediately tells us that we can actually, instead of considering C to be on the unit sphere, I can assume that C is in a projective space because I can identify C and minus C. And I can also think about this space, as the space of orthonormal projectors onto the subspace spanned by this C. This is a formulation that we're gonna, the representation of this space that we're gonna use. So how can we write down an orthonormal projector of onto a one-dimensional subspace? Well, it's a matrix, C, big C, such that C squared is equal to C, and the rank of C is equal to 1. And we know these were the outer product matrices here, okay? So what this says is that this problem truly is an optimization problem over the space of rank 1 matrices, symmetric rank 1 matrices. And in case we have a vector observation signal, we use a constraint that C belongs to the Stiefel manifold, and you can see that if I replace C by theta C, where theta is an orthogonal matrix, so what does it mean to be an orthogonal matrix? Theta belongs to SOP. If theta transpose theta is equal to the identity here of size P. And if I change C to, or say C transpose to theta C, sorry, the opposite way. C to theta C, you can see again that we have some invariance. So this tells us that the optimal sensor problem will only depend on the span of these C rows. Does not depend on the actual value. So it is truly a problem that's defined on the, well, the set of p-dimensional planes in Rn. So it is an optimization problem on the Grassmannian GR of NP. Okay? So this is a set of p-planes in Rn. Oh, okay, little interlude. So this is Mr. Grassmann, and he actually never could find an academic position. So he subsisted by teaching high school math and Latin for a living. And he had nevertheless a rather groundbreaking contribution. And he very much looks like a Latin professor. Okay, so how are we going to represent the Grassmannian? As I said, we're going to decide we choose to represent the p-dimensional planes via an orthogonal projector onto this space. So C is positive definite, C squared is equal to C, rank of C is equal to P. This defines a projector. Okay, how are we going to represent now the set of such matrices? We're going to use this representation. So we're going to say that the Grassmannian of p-planes in Rn is a set of matrices theta, lambda, theta transpose, where theta is in SON, and lambda here is a diagonal matrix with p entries 1 and all the others 0, where the p1s are is actually irrelevant because this is just washed away by the theta. And you know, just write this explicitly, that C squared, now this is C, is equal to C, and obviously by construction, if this has only P, this diagonal matrix has P entries on 0, this will have rank P. So this is the way we're going to represent the Grassmannian, the set of matrices that we can write in this way. Okay, so just rewriting the problem again, we wish to minimize this function. Now C belongs to the Grassmannian, and this is our SNR. Okay, so how to think now about how to optimize this function? So you know that the gradient of a function j, classically, what we learn in I'm not going to say high school, I'm going to say middle school, is, or in college, is that the gradient is a vector of partial derivatives. Now we have a function in a manifold. We cannot quite use this because this is not well defined. So here is how to think of the gradient of a function defined on a manifold. First of all, you may remember that the gradient can also appears in the definition of the directional derivative. Here you see x is a point, v is a vector. If I look at the differential of j in the direction v, I can write it like this, and you know that, well, by the chain rules given to us by the gradient transpose here acting on v. Okay. Now, okay, here I could also put, if I want, a positive definite matrix, and I can think of this as what some people call a Mahalanobis distance, or just a different metric. And I can now define the gradient according to this equation. The gradient, grad j, is the vector such that if I were to compute the directional derivative in the direction of v, it is equal to grad j inner product with v. So think of this as directional derivative, this is inner product. Why do we want to do this? It's because directional derivatives are intrinsically defined. You can always define a directional derivative, you cannot always define a gradient, for that you need a metric, but this is fine. So this would be the equation defining the gradient. The minimizing property of gradient flows, by which I mean if you solve the equation x dot is minus gradient j, are we going to tend to a minimum of j, still holds for this definition of the gradient. Okay, so now this easily extends to a more general setting. If x does not belong to Rn, but x belongs to a manifold, the only thing you change here is that instead of having all v in Rn, you consider only the v's here which belong to the tangent space of the manifold at a given point. So this is just a slightly more complicated definition, but it's not too difficult to work with. And we still have the nice property that we will converge towards a minimum of j, provided that j has nice properties. So this is our program somehow. We're going to compute the gradient of j on this manifold, and then analyze a function to show that it has nice properties. Okay, so we mentioned tangent space, so I need to find the tangent space of the Grassmannian. So standard computation shows that the tangent space at a point C, at the matrix C here, is given by this vector space. You can see that this is a vector space. It's a space of matrices C bracket omega, where omega is skew symmetric, by which I mean omega transpose is equal to minus omega. So this is little SON to the algebra of skew symmetric matrices. Okay, so the space of all such matrices gives me the space of all directions in which I can move while keeping the property that I'm a rank P matrix and symmetric positive definite. Okay, now we'll need to define an inner product on this space. Okay, how can we do this? So this is a K, this is frac K for LaTeX. So let Kn be the vector space of n by n symmetric matrices. I define the operator at C, this is a very common notation, to take a skew symmetric matrix and then take its bracket with C. And you can check, this is a one-line computation, that if you take a skew symmetric, take its bracket with a symmetric matrix, you obtain another symmetric matrix. Now, observe that this operator at C, from here to here, is not invertible. But we can make it invertible, and you're going to see why we want to do this, in a fairly trivial way, by just restricting here to its image and modding out its kernel. So that will make everything invertible, right? So we call this operator at bar of C. Okay, so to summarize this slide, this is a tangent space, space of perturbations that perturbation that keep us on the manifold here, the Grassmannian. And this is the, we're just right now making sure that this operator is invertible. Okay, how are we going to define a metric? Well, there is a kind of a nice intrinsic, or if you wish, God-given matrix on a Lie algebra, which is what's called the killing form. And it's just a trace norm. If you take two skew-symmetric matrices, the killing form k of omega 1, omega 2, the bilinear form, is proportional, there is a coefficient here which I can ignore, to minus trace 1, omega 1, omega 3. So you see that because omega 1 and omega 2 are skew-symmetric, you can just think of this as a Frobenius norm, actually. It's a trace norm of the Frobenius norm. Now, the normal metric, that's a metric on the tangent space here, is what you really want to do is use this metric. So what you do is that you want to invert for x, sorry, let me write this here. I mean, you remember that all the tangent vectors were of the form x is equal to at c certain omega x. If this is a tangent vector, or this is a vector on which I want to define inner product, I can write it of this form. So what I want to do is kind of cancel this guy out, take an add inverse. But inverse was not well defined, but add bar inverse was well defined. So I'm going to define the normal metric as this. I'm going to take back my vectors to their original space by undoing add c, and then take the trace. And you can show actually that this metric is well defined, positive definite, and non-degenerate.
So the inverse gives you an equivalence class, and
yes.
then this operation lifts.
So the inverse, you can think of it giving you an equivalence class, but it's a very good question. Here, notice that I modded out, right?
Yeah.
So that gives me a unique representative of the equivalence class. But you can say, well, how did you mod out? That still gives you an equivalence class. All the construction, either you choose, here a way to mod out by saying you take the orthogonal projection onto the for the killing form, which is non-degenerate here. But actually in the computation, you can show that everything you do is going to be true for the equivalence class.
Okay.
So it's not even important here. Yeah. But even if it were not the case, you can still work with this. That's the point here. And so this metric was introduced actually by TI in '82 and was used before in engineering application. The twist that we have here is that we're forced to deal with matrices C that do not have distinct eigenvalues. In the case these people have looked at before, the matrix C here had distinct eigenvalues, and that allowed you to not have to deal with this add bar, because you can show that if you look at the operator add C, its eigenvalues are the difference of eigenvalues of the matrix C. These are the eigenvalues of this operator. So if all the eigenvalues are disjoint, are distinct, you have only non-zero eigenvalues and you're invertible. In my case, I have plenty of eigenvalues 1 and plenty of eigenvalues 0. So this operator has a huge kernel. That's why I needed to do this. But it works, and there is no problem. So, okay, I'm going to make a comment about this a bit later. Here, Mr. Wilhelm Killing. What's important about him is that he wrote the greatest mathematical paper of all time. And I have to admit that I have not yet read it. And this is according to A.J. Kalman, who I think was a historian of science at Princeton I think this was written in the 50s or 60s. But this work of Killing, where he defined a killing form that made the classification of Lie algebras possible, is indeed a kind of a turning point in the field. And there is something quite nice, is that this is, I mean, he seemed to have grasped the importance of the fact that this metric was introduced with just the data of the Lie algebra. There is nothing additional in the definition. Okay, so now we can compute the gradient using this metric, the normal metric. It satisfies this equation. That's the equation we had at the beginning. For all perturbation in my tangent space, I need the directional derivative of j in that direction to be the inner product of the gradient of j and x. This holds for all x, and this defines the gradient of j. Now, you remember what k kappa n was. You can try to solve this equation. It takes a few pages, but it is doable. and you find that the gradient is exactly this vector. So that was our first contribution, sorry, statement number 5, I think, that was it, where M satisfies this equation, and K and R satisfy these two equations. And now we're going to quickly see why this holds. Let me make a comment here. You can wonder, or you've seen that a lot of the statements I made were statements about the function J, right? The number of minima of J and things like this, and the signature of the Hessian at these points. So the number of minimum of a function, of course, is independent of the metric we have under the underlying space. So why did I choose this metric? I could have done this computation with a different metric. I should have obtained the same result. I should say here that we work with this normal metric, even though it seems to be rather complicated. In fact, it has actually a lot of very nice properties that make explicit computation possible. Had I chosen a different metric, I may not have found such a compact form for the gradient, or the computations would just have been impossible. So choosing the metric was quite important, but at the end of the day, all the results are independent of the metric. But it's a worthwhile effort here. Okay, and we said that the observation matrix is critical if the span of C is an eigenspace of M. Now it's easy to see that this is the case. So a critical point is a zero of the gradient. In order to have this zero, you can show that it's necessary and sufficient to have C bracket M0. You can say, what about C multiplied by all this zero? And the answer is no. This is only this that counts. That requires a bit of work. But so C is critical if and only if C bracket M is 0. Using some properties of the Riccati equation, you know that the matrix A minus gamma ck is stable. That's a property of the Riccati equation. I mentioned A minus ck because it entered in the definition of R. We had R was a solution of the Lyapunov equation, A minus gamma ck R plus R times this guy again, plus L was equal to 0. And you can show that if this matrix here is stable, R is unique and positive definite. So if both K are positive definite and symmetric, so is a product. If both K and R are SDP, so is their product. And then you can show that if two symmetric matrices commute, they have to have the same invariant subspaces. So this is how we found.
You said at the beginning there would be some restrictions on gamma. I don't see it in the critical point equation, but is it related to your statement about the Riccati equation?
So we require, gamma to not be too large, and this
so
comes from the proof, because
yeah.
the gradient has a nice compact form. Right now, all of this holds, I mean, as you kind of point out correctly, for all gammas.
Yeah.
The following statements are going to require that gamma is not too big. We can even characterize how big it can be. It can in general be rather large, but it does not hold for all gamma greater than 0.
But intuitively, in your kind of polar decomposition or whatever, gamma, I mean, I'm just trying to remember, why did you introduced gamma at the very beginning of the problem, but was it more of a nuisance parameter, or was it telling you something else?
Oh, so intuitively you can think of, not intuitively actually, what is gamma is a signal to noise ratio.
Ah, okay,
Gamma
that's
small,
what it captures.
yeah.
Yeah, I got it.
Gamma small is a small SNR.
Got it.
And we can here work in the small SNR regime. But as you just mentioned, this holds for all gamma. There is no assumption of gamma small in this case, not even an assumption of A stable. That's always true. So here, gamma small enters, and A stable enters, and this is about the critical point of J. So we have its gradient. How many zeros does it have? Well, it has exactly n critical points, and they have D signature. So these were the number of negative eigenvalues, positive eigenvalues, and 0 eigenvalues. So all of them are non-degenerate. We have plenty of saddles. We have one maximum and one minimum. So J is kind of a nice, a nice function if you wish. You have one minimum one saddle of each type, and one maximum, one saddle of each type, one minimum. And you can also characterize, by doing a little extra work, the critical point of a certain signature, their projection matrices onto the pth highest invariant subspace of the corresponding M. But so this tells us that for gamma not too large, you have only one minimum. So you have a unique optimal sensor. And you know that if you have a function which has a unique minimum, when you do a gradient flow, with probability 1, it will go to this minimum. It will not get stuck at a saddle point, and certainly not go up to the minimum, to the maximum. Okay? Unless you're very unlucky when you choose your initial condition, and in practice you don't even see that. So this is what tells us that the gradient flow will converge to the optimal sensor. The analysis here of this, and why do we need this for gamma small? It's because let me go back. So for that I need to analyze the Hessian. The Hessian is actually quite nasty. And we can show that the Hessian is analytic in both C and gamma. And we look at the development in terms of gamma, and for gamma small, we can analyze it. When gamma becomes much larger, you have two terms interacting, and at some point, the second term will overtake the first term, and you will not even have these nice properties. So when gamma is larger, you don't even have a unique minimum. So you can find matrices for which this is the case. You just run the gradient flow, which is true independent of gamma, and you just find numerically several local minima for J. Okay. But when gamma is small, this is always true. Okay, the case of orthogonal observation vector is a bit, is actually very clean, but is a bit hairier to define. There is a bit of combinatorics into trying to count the number of critical points. So one definition, if D is a positive integer, I call a partition of D with P parts, the datum of P positive integer whose sum is D. Partition is distinct if the MIs are distinct, pairwise distinct, pretty natural. A restricted partition, restricted here by N, is such that none of the parts are larger than N. Okay, so here is P6 of 2, 8, it's just 2. You can write 8 actually as 6 plus 2, 5 plus 3, 4 plus 4, or 7 plus 1. 4 plus 4 is out, it's not distinct. 7 plus 1 is out because 7 is larger than 6. So you're left with 6 plus 2 and 5 plus 3. Okay, so you have tables for these, you have recursions for these. They've been somehow studied before. They're related to the Q binomial coefficient. Okay, and we need these actually to classify, to count the number of critical points of our function J. So if D is NP minus P squared, that's a dimension of the Grassmannian. The number of how many critical points does J have, N choose P, that's a lot. How many of each signature? So you fix N plus and N minus. They have to sum to D, of course. How many critical points with this signature do you have? Well, this is the answer. The restricted partition by N of P, NP, N plus this guy. Okay, that's the number of critical points of signature N plus N minus, and I should write here 0. So what is nice again is that you have a unique critical point with signature D0 and 0D and also D's. We care about this one because D's corresponded to the minima. All eigenvalues of the Hessian negative. So even in the vector case, we have a unique minimum. Okay, so here, basically, I tell you again about the proof, but I just said a few words. You can write the positive definite solution of the Riccati equation and everything that's based on it, the function k and so on and so forth. You can show it's analytic in both C and gamma. And you can show that for gamma 0, there is a finite number of critical points. Now we want to make sure that when we increase gamma, we keep these properties. So we have to compute a certain derivative and show that this derivative is non-degenerate. So we're going to keep the property that we have for gamma equal to 0 for gamma larger. So we can do this. And the last step, so we know that the behavior for gamma small is going to be similar to the behavior at gamma 0. Now we need to analyze the behavior of J for gamma equal to 0. That's a very bad SNR. And this is what we've done to find all of these, the signature of the critical point and their numbers. So this is how the proof works. So in some sense, the proof is very natural. You just write down the problem as an optimization problem on a manifold, and you try to, and you just solve, you analyze the function, find the gradient flow. Okay, so I am actually almost right in time. We have a few minutes for questions. There are more. Summary and outlook, so extensions to the infinite dimensional case, of course. There's been a result proven very recently, actually in 2016, showing that if you take a finite dimensional problem and you let it, you increase the dimension, let it converge to infinity, and you have an optimal design, optimal sensor for each finite dimensional version, the sequence of optimal sensors will converge to an optimal infinite dimensional sensor. So I've not yet looked at the result, but this would basically tell us that we can use the work presented here to obtain optimal sensors for infinite dimensional systems. So this is rather interesting, at least in application, because if you wonder, where should I put the sensor to measure the temperature in this room? You have the heat equation telling you where, the evolution with an infinite dimensional equation, a PDE, how the temperature evolves in the room, where to put the sensor in order to get the best estimate of the temperature. This is a type of question we want to answer. Right now, what happens is that the contractor puts the sensor somewhere convenient for him. If you find that the optimal sensor should be somewhere, well, probably this is still going to be the case. Even in a few years, it will be convenient for the contractor.
The optimal one is in the middle of the room.
Yes, if it's just here, levitating, that might be difficult. So we need to put some constraints on where we can place the sensor. As I said, I required, when I had several sensors, every of them to be orthogonal, to give me orthogonal rows. This is not ideal, because it might be, if I have two sensors, perhaps the best thing to do is to both put them in the same place, i.e. put all your resource measuring this variable. So I don't quite know yet how to solve this problem. It's a more difficult problem. How to handle the case of A unstable? Well, I can tell you the issue with A unstable is that the function J is not bounded. Right now, J was a function of the compact manifold, the Grassmannian, to the real. If A is unstable, the function J has poles, has even ridges of poles. And these poles will just split the domain in two. So right now I have a gradient flow that tends to the minimum. The gradient flow is not going to go above something that goes to infinity. So that's a bit of a problem. But it's not even that simple, because the Grassmannian is not all of them are orientable. So even if you have a ridge, a continuous ridge of infinite valued function, where the function is infinite valued, it does not disconnect the space. So let me perhaps try to say this again. If you have a sphere and imagine a number of infinite values for your function, the gradient flow will not be able to cross it. If your space is not orientable, it's not the case anymore. You have a number of infinite values here of codimension 1, you can still go around it. So the gradient might still converge if A is unstable in some situation. So what it says is that we even need to care about the eigenspaces of A, and then it becomes extremely complicated. So I don't know if we're going to have a good understanding of this case anytime soon. And this is it. Thank you for your attention.
Questions?
Are there additional questions?
Just to the third point about SNR, is there any intuition? What does the intuition achieved from the all eggs in one basket? And I'm trying to understand if it's So it's not just a consequence of your analysis, because you mentioned that if you simulate in the high SNR environment, you lose unicity of solution, or you get a bunch of local minima. So what does it tell you about the kind of well-posedness of the problem, and how does that influence the question of the least gamma star for which you would recover something of rank 2?
Yeah, that's a very good question. So basically you're asking, when you have very precise measurement, you may have two sensors which are locally optimal. Two distinct sensors that are locally optimal.
Yeah, what does that mean, I guess? Or I was trying to get my head around whether that agrees with intuition, or whether should that be surprising, or is it somehow... I mean, I understand that things will be... You're inverting a system, and that once there's relatively little noise, you're going to have stability, not control stability problems, but somehow in terms of an inverse problem, it starts to feel like a very unstable inversion. But is there more intuition there, or am I getting the intuition right, or maybe not?
To be honest, I just don't know. I mean, I can find stories that would go one way or the other, so which tells me I don't really have a full understanding. You see, you want to say that when your measurements are very precise, you can kind of ignore the fact that you had noisy measurements. And what really matters is A. And how A and G, I've not written G in a while, but G was how the noise was entering in the dynamics. It was GBW. That this is what will matter. Yeah. And so according to how A and G are distributed, you may have several optimal sensor or no. You just don't know. But it depends on how they are.
The observation equation ceases to be important.
You know, it's useful for the estimation procedure, but it's not. This matters more. When you have a very low SNR, then I just don't know. I have, as I said, several stories that go one way or the other.
I guess one way to think of that one is, say you want to measure the temperature in the room, you put one sensor in the optimal place. You have another sensor, what do you do with it? Do you find another good spot? Actually, no, you just put it in the same place and get a much better signal to noise ratio in that optimal spot.
Well, but suppose that you might make it extreme, you don't have any noise at all, you just have this equation there. Then you certainly don't gain anything by putting the two sensors in the same place, because they will just give you the same result. So then the optimum has to be, it must be some better placement, but...
Yes.
But I don't have a good intuition even of this equation without any noise. I mean, since you only observe one projection of it, of course it is still a non-trivial problem. So I don't have any intuition really how one should do in that case, extreme case.
It's I mean, there is something. Well, a very recent result, very similar to this. I said a word to Sophia about this earlier this week. This is magic. If we look at the case, and even the lights turn on, without dynamics. So this is the same equation as we had before without A. So just driven by noise. Same problem. Cx dt plus dv. And so what is the optimal C in this case? It has a much cleaner form. But again, I don't have a lot of intuition about it. You find that C is, well, proportional. Sorry, let me write this with a little b and this a little c. So I can write that C is equal to C transpose and big B is equal to B transpose. So this is a bunch of columns driven by noise giving me my process. B is the outer product of these columns. It's going to be the covariance of X. Right? You find that the optimal C, optimality being defined as before, but without the constraints of orthonormal, is actually proportional to the cube root of B, which is really quite strange. But so we do some smoothing, so some compression of the eigenvalues of the covariance matrix, but we keep the eigenspaces. So we're calling that the cube root here. What we do, we write this as u lambda u, take the cube root of the eigenvalues. So we penalize, well, 1 over the cube root of the eigenvalues. And this works for every C, meaning they don't need to be orthogonal in this case. That's just the optimum. But as far as I'm aware, whenever we add an AX dt here, obtaining a closed form solution is just impossible.
Is there a way by continuity to see what happens when you consider the space of stable A and let their norm shrink to 0 or something? Is that not?
We looked at this. That's, I mean, it's the sort of thing we looked at, yes. I mean, it's just not continuous. The limit, depending on the A you choose, will affect
you
things
can't get there. Yeah,
very, very strongly. It's just not continuous with respect to this parameter.
Right.
Yes.
But then I have a similar question. Since you have got your, you have a problem if you have a high signal to noise ratio, but you get nice result was small. But what happens if the signal goes to 0? I mean, if the signal is exactly 0, of course you can't don't get anything. But asymptotically, if the signal noise ratio goes to 0, will your equation simplify them? Can you somehow linearize them also?
Okay, so we're talking about the general case here?
Yes.
Yeah, because you had one slide where you were showing, for example, that when gamma is equal to 0, then something simplified. But
Yes.
yeah.
So you're thinking of the case gamma is infinity?
No. See, gamma wasn't gamma signal to noise. Which was gamma?
Yes, so gamma was the SNR.
Yes, the strength of C. Yes. So if you let, I mean, if you put gamma equal to 0, it doesn't depend on C at all. But if you let gamma be very small,
Yes.
and you want to find optimal C here, you have your equations and so on.
Yes.
So do the equations simplify you if you let gamma go to 0?
Can you rescale
Oh,
and
yes.
somehow let gamma approach 0?
Yeah,
but
so
not get there?
that was indeed the
That's what
full
you did
technique.
with it.
Oh,
Is
yes.
that
what you
this
did.
way? Okay,
Yes.
yeah, yeah.
So we showed it was analytic in gamma,
Mm.
and we could analyze the behavior for gamma very small.
Okay.
And then
yes.
I know it
see.
extends. We didn't
Okay.
have to show that it holds for larger gamma. So
No.
this is what we can do.
Yes. Yes.
And we even have simulations that try to guess how large gamma can be. And it's actually not too small in practice. Of course, depends on A and B and things like that.
Yes.
Do you have any numbers for that actually?
For how large gamma can be?
Yeah.
Like 1, 2, 3. So, like if you take A to be random matrices,
Yeah.
the way I sampled my A's to be stable was by rejection sampling.
Yeah.
I just took normal 0, 1 entries, compute eigenvalues. If it's stable, I keep it, otherwise I reject it.
Yeah.
With this sampling for A, gamma can be, 1, 2, 3, sometimes all the way to 10. But, not more than that. So, I mean, in order to analyze this properly, we did a little bit of that in the paper. You need to compare the size of gamma to the eigenvalues of A. This is somehow the correct things to compare. And it can be quite large. Yeah. I mean, you can even write an equation that tells you how large gamma can be, because this is, okay, what we have is the Hessian of J is going to be a sum of 3 terms, one linear in gamma, well, a sum of plenty of terms. But, well, I want to make sure that this term here is a dominant term. So I know how large gamma can be until this term overtakes this term.
Right.
Both are positive definite terms.
Yeah.
So this is how you can actually find it, and you can just write down explicitly what these 2 terms are, right when they have an eigenvalue in common, but that's close to impossible to solve.
And regarding the eigenvalues of A, that's something about the signal to noise ratio of the system relative to the dynamic, the house.
A will affect that, right. So if A has a lot of very negative eigenvalues, it will drive the system very quickly to 0.
But then the power of A is large somehow, which is
Yeah, it just kills
Yeah.
all the
and
noise
all
that
the
you
other
get here.
effects. Yeah.
So if you just didn't have anything here, the steady state will be such that the distribution of X is very
Goes
concentrated
quickly to
around
0.
0.
No problem. Thank you. Any other any questions from you? You're good. All right. Let's thank Adi once more. Thank you. That was fun. We can remove you from being on air.